how it, so shear wall can have openings, you can stiffen the bracings, you have different systems. So this is an example. In 1895, Chicago is known for this, Reliance building. Then we have, this is a flat-run building. See the mechanisms where they have actually done. Then the frame tube system, so this external framing is there. The Sears Tower, World Trade Center, which is now collapsed actually. And then you have systems where you have X braces outside to stiffening. The whole idea is these are all existing structures, and the idea that they have used is this. This is the idea. So you just do that, and you come out with these innovative structures. This is in Japan. Then tube in tube is another. You can have bundled tube. The Burj Dubai is a bundled tube system. You see, this is in again Chicago is known for this. There was an engineer called Faizlur Rahman, who was a Bangladeshi engineer, and he designed many of these innovative things. So all this requires is proper alignment, proper clustering of the towers to improve the stability. In fact, this is how you can have grids in different forms up to one level, full rectangle, then slowly you can discontinue, and the top only triangle. So this is a building which actually shows how the structure system is bundled to improve the stiffness. So I think in his study, Anchuri has taken different forms. He has called it different forms. So he has made some studies. I'll just show you what the study says. So this is how he got the idea from this, the DAG grid. We are all familiar with how when a force is acting on a triangular portion, how it gets distributed and what is the effect of shear force, what is the effect of gravity load, what is the effect of lateral loads, how it influences the force flow. So all this keeping in view, he has designed it and has come out with different forms, and he has tried to analyze DAG grid structures for high-rise buildings. And he also studied the mode shapes, because now as you go tall, the dynamic behavior is also equally important. So different mode shapes, and then he has tried to do it. He has also kept in, because he's an architect and a practicing engineer, he has also kept in mind the challenges like cost, erection, fabrication. These are things that we need to do, sustainability also. And this is how, with some example, he has done it. Vertically planned spaces and all that. And efficiency of the space is very, very important, because how to use it, the functional utilities. So the bottom portion is for reception, the top 10 is hotel lobby, restaurant, spa, residential, like that. Keeping in view the requirements, functional requirements, you have to design that, and that requires proper planning, shapes and all this. And he has done a study of the weight of steel with a number of stories, and he has come out with optimum structure. See, when we say optimum, we are talking about two things. One is structural efficiency. The next is the structure, how structure is efficient. You don't want to waste materials. Everywhere it should have proper thing. So this is how, today you can find the artists coming out with different ideas. But all these have got structural basis to reduce the loads, to reduce the forces, so that there is a material utilization less. And also it looks very good, elegantly. Somebody seeing this building, looks like an iconic building. So what is he doing? He's trying to improve the stiffness. And he knows the stiffness of the system necessary with weight. So an ideal structural system could be that in which steel required to carry the gravity load. The gravity loads are just the vertical load and dead load plus live load. And the lateral load could be due to earthquake or due to wind. In these buildings, wind load is important. So, whenever there is a wind load, we have 33% increase in the stress levels and all that. So we have to do in such a way, optimize that the gravity load is sufficient, and the design is like this. So this is how we do it. And in fact, a lot of, so we have to keep in mind, whatever we do, the structural stability. When I'm talking about structural stability, I think you can understand. We are talking about deflection, we are talking about durability, we are talking about strength and rigidity. So structure with adequate strength will not collapse, but excessive flexibility is also not good. Too much flexibility is also not good. Just an illustration, okay? So as a professor, you don't have if you have time, you do all these things. It's nothing to do with this high rise, but it gives an idea. So there is definitely a relationship between form and efficiency, so you get all these interesting things. And then we started doing all these experiments, different grades and all that. We used, which software was it? ETABS was there. And of course now we have softwares available, so we can play with it, do really wonderful things. You come out with very nice things. So this was the idea, baseline, doing that, then slowly modify the shape and again study the analysis. advanced. He did a non-linear dynamic time history analysis and using ETABS. And then he's validating the results. Just doing the running the computer is not enough. You will have to validate the results. So finally, he used the cantilever analogy and tried to arrive at the various. And it's very interesting concept in optimization. When you apply a load, you get a deflected shape. So what they do is, they reverse this profile. So automatically, this is coming like this, you just reverse it. Automatically, there is more stiffer, and that is beneficial. So the idea is you take this truss optimization. From that idea, he has arrived at many things. And also using this higher grade concrete. You'll also notice he has studied different structural forms with different opening sizes. So these are the actual studies that he has carried out. I don't want to go into the study because we don't have time for technical discussion, but yes, he measured the deflection, drift, and other things, and this is what he got. This is a graph showing the maximum drifts due to different load combinations. That is the 1.2 dead load, live load, and wind load. And the story displacement is what is critical, and he has tried to study the story displacement for different models, and he finds that, the model 3Y is a maximum drift. So like that, he arrived at certain consideration, and he came to a conclusion that, different structural systems are suitable for different heights. So this is how now the future of high-rise buildings is going to be. Very soon, India is also doing it. We are a lot of in Delhi actually district. So you have to make sure, this earthquake is not a critical ground. It is a wind load that is critical. Today, because of software that we have available to us, virtually today limitless 3D shapes can be generated and analyzed. But the condition is there is a fabrication limitation or implication and cost. So geometry has a major impact on the cost of building. Some simple buildings are very complex, but some complex buildings can be very simple. These shapes look complex, but they are very simple to actually erect and do it, okay? So this is how some of the international buildings I took. You see the idea here. This is how the bracing has been done. And interestingly, if you see the mode shapes, so the bracing provides stability in the upper part, and then the lower part is using concrete to improve the stiffness. Unfortunately, the figures is covering the text. So using the simple structural concepts, you can arrive at it. And this is in the Middle East, you can see this. The building has been twisted with external bracing to reduce the drift. And this is the mode shapes. So everything has to be done. You just cannot do gravity analysis. You have to study the mode shapes, arrive at the configuration, then only decide this is good. Then you can come out with interesting ideas. Again, this is in somewhere in Dubai where I had opportunity to visit. And these are all his studies, results of his studies, which he has made with different ETABs. And based on these results, he has arrived at certain computational form generation, some methodology for computational form. He has the tools that he has used for structural analysis, mathematical programming, geometry. All this is required now if you want to really optimize the structural behavior. So architects and structural engineers have to join, integrate, and then arrive at the thing. Always there is a conflict between architect and a structural engineer, but Anchuri is both an architect and a structural engineer. I don't know how he's managing inside the conflict, but yes, he's coming out with wonderful structures. So I told you modifications, other things. So I'll show you some final conclusions. I'm sorry I have to run fast because of the time the chairman has told. So this is another idea of topology optimization, how we can use for high-rise buildings. And you can take many of the ideas from aeronautics. In aeronautics, you deal with wind. So, and to arrive at the move to adaptive structural forms. And there are different form generation methods I showed you with examples. And in this case, he has done so many studies, and these are the results that he has obtained. And this has now been worldwide appreciated. Recently, it was published in the ACECON conference, Indian International Structural Engineering Conference. It was received very well, and a lot of queries are coming, how we have done and all that. Keeping in mind that we have to do all these codes also has to be taken into account. Otherwise, people will not accept your designs. So this is just running. So the results show that optimization can be done by changing the form based on displacements created due to lateral loads. The maximum story drift is the important criteria. The analysis can be carried out on various footprints with different corner modifications. So The design issues in tall buildings are efficiency of systems, stiffness, member depths, balance. So no one system can work. You have to work out different to arrive at the most optimum. But what definitely helps is good preliminary design, and optimum will lead to better fabrication, erection costs. I showed you a small corner modification can reduce almost 8,000 tons of steel. So tall buildings today present special challenges to designers and construction engineers, and the challenges are mainly from wind and seismic loads. So in coastal areas, maybe we cannot do it, but yes, in central areas like Hyderabad, yes, it's a good. So the idea is reduce the strain energy, displacement, drift, and optimally utilize the concrete. So thank you very much, and I hope I've maintained the time. Thank you.
So, a few questions. Please, sir.
Yeah.
Sir,
So the paper is available in the computer for taking away.
right, sir.
Yeah.
Sir, you are saying that these structures, anyway, steel structures, proximity to the seashore, it will be difficult, I think, to use it.
Seashore, because the build loads are very high, as high as
For
270
that,
km.
and how that carbonation and this
Corrosion is
will be taken care.
now technology has come to improve the durability and all that.
But I have seen it in Amaravati, now 4 towers, they have started, of course it is stopped and now again restarted. Those 4 towers they are doing with the diagrid system.
What is the height?
That is 40 stories, sir.
So 40 stories is very less actually.
Yes, sir.
We are talking about, Burj Dubai is 1 kilometer high, that is 990 meters.
But it is nearer to the river only. That,
River is not good. See, there are ways of reducing the corrosion. Today, you can use cements which are corrosion resistant, steel which are different treatments are there. Corrosion is not a big issue now.
I've seen that the core they have made, sir. So peripheral they have given the diagrid, sir. Core with the RCC structure only they have gone for it, sir.
Yes. There are a lot of techniques. So see, Anchuri in his thesis has tried so many examples. When you're doing a PhD thesis, you can try, the guide will say, try this. And finally he has arrived at a conclusion. And this was well approved. You want to add something? Yeah.
Sir, thanks a lot. Actually, I'm so kind of you. You presented in a very excellent way. Sir, you said how this architect and engineer, how those people they think, and sir, just to have some, I will add just how we started, because he gave that idea. I will give one small experiment. You cooperate. Can everybody stand? Please. Away from the table. Don't take any support. Away from the table. And then just close your eyes and savdhan. Savdhan. Savdhan means savdhan. And close your eyes and observe your body for 10 seconds. If your upper body is swinging left, right, or straight, you are in a stable position. In fact, if you are not, then it's a problem. So, Saudhan maybe just observe. So there is a sway and a drift and deflection. You are there. Now there is a spread foot method, Vishram. Now you try just again close your eyes and try to move your body upper part. It will not move. You are stable. So when you are in Vishram stage, you are stable. So to what extent you have to spread? So Eiffel Towers is a very wide area, but with the same geometry, with the same usage of the upper floors, which is very costly. So being an architect, energy efficiency, space efficiency, and the comfort that we integrated with the help of the sir. So I could achieve that. Thank you.
Excellent, sir. Actually, explained in lucid form, so in a simple terms. So nice of you.
He has to become professor now.
Any other query? Okay, thank you, sir. You guided well, Dr. Anchuri. Our next presentation is by Mr. Hanan. Mr. Hanan, okay. It is on life cycle analysis of sugarcane bagasse as blended cement, a case study of AP State. You have 8 minutes, so fine.
Good afternoon, one and all. My name is Hananaj, a research scholar from Bitspilani, Hyderabad campus. I'm working under the supervision of Professor Bahruddin A and Professor Srinivas Sapari. Today, I'm here to present my work on the topic Life Cycle Analysis of Sugarcane Bagasse Ash Blended Cement, a case study of Andhra Pradesh state. So today we are revolving around these topics. So starting with the motivation behind the study, as we all know, is one of the most common building material that will continue to be in demand far into the future. A world without concrete and its dominant pre-ordinary Portland cement is hard to imagine. So the dependence on the OPC is such that the global cement production is 4.1 billion tons, and India is the second largest cement producer in the world, which accounts for around 9.5% of the global capacity. So the global cement production has grown rapidly. Industry has become the third for the anthropogenic emission of carbon dioxide, which accounts for around 7 to 8% of the global carbon dioxide emission. So what can be done in order to reduce this carbon dioxide emission? So as a solution, the need for the supplementary cementitious materials comes into the picture. So in order to reduce thereby creating a sustainable environment, the need for the SCM is the construction industry. So in my study, I incorporated sugarcane bagasse, that is agricultural waste, as an SCM source. So sugarcane generation combustion boiler from the sugar industry. So after crushing the sugarcane for the extraction of the juice, the discarded fibrous matter is called the bagasse, and this bagasse is used as the fuel in the cogeneration boiler, and the residue after burning is called bagasse ash. So India is the second largest producer of the sugarcane in the world, and it is simply directly discarded to the nearby landfill, which causes severe environmental pollution as well. So using this agricultural waste in the concrete, which paves an alternative solution to its disposal. So by using this agricultural waste, a life cycle assessment is employed in my study. So basically, what do you mean by a life cycle assessment? So it's a technique to environmental impact and its potential consequences associated with a product or services is the life cycle assessment. And so it is a great tool in which helps to guiding the selection of the alternative building materials to show which combination has the least negative impact. So main objective of my study is to perform the life cycle assessment of SCBA based binary blended concrete in the and conduct a comparative analysis of the impact of SCBA based binary with the reference control concrete in the state and to raise the efficiency of SCB improving environment of binary blended cements. So the mixture details of the four combination used studies depicted in the table, and the values are kilogram per meter cube. Going through the methodology, so the first phase is the goal and scope of the study. So the primary aim of the study is to investigate the environmental impact of the SCBA based binary blended concrete and the reference concrete in the AP state. So the current study employs the SCBA generated from the 28 mills planned in the AP state, which produce around 4,000 tons of SCBA annually. So here 3 scenarios were considered. So in the first, second and third scenario, the quantity of the available SCBA was considered completely assumed to produce 10-20% of the SCBA based binary blended. The respective reference concrete where that is without SCBA were named as R1, R2, R3. So based of the SCBA, the volume of the SCBA based blended concrete was calculated. So here the graduated LC approach was used, and the system boundary is shown in the figure, which includes all the emissions and the energy utilization for the raw material acquisition, the transportation, till the concrete production stage was considered for the study. Unit processes within the system boundary which are required to create a product system. And the third phase is the life cycle assessment stage. So here recipe, midpoint and endpoint assessment were used, and the OpenL software was used for the analysis as well. So the final phase is the result analysis and result interpretation stage. So moving to the results and discussion. So environmental impact of analyzed using the recipe methodology. Then here the results are midpoint impact results were shown in the figure, which indicate each contribution of each raw constituents in the product system to the environment is depicted here. And among the different impact categories, the climate change impact category that leads to the global warming, which is driven from the carbon dioxide emission, is shown as the most detrimental one in the construction industry, and Ceylon, which is responsible for 31 to 93% of the total impact. So the graphs which clearly shows that environmental impact is very high for cement in all the impact categories, but except for the terrestrial ecotoxicity impact category, that is TET impact. The transportation is the primary or key contributor to the terrestrial impact category. Which directly damage organisms. Results of the endpoint impact categories were depicted in the figure, and endpoint impact of protection level, that is quality of ecosystem, human health and resource scarcity. So it is clear that the reference R2 to R3 are the most significant impact in all the three domains, and also the B30 blended concrete is 26.7, 26.5 and 22% lower than those of the reference concrete in the ecosystem, human health and categories respectively. So moving to the conclusions, SCBA based binary blended concrete exhibits a reduced environmental impact in both the endpoint and midpoint impact categories with respect to the respective reference concrete. So cement contribute to higher climate change potential around 93% in the reference concrete, and transportation is the primary contributor in the TET impact category, and the reference concrete had a greater environmental impact in the SCBA based. B30 concrete exhibit a better performance in terms of ecosystem quality, resource scarcity and human health when compared with the corresponding concrete. Hence, the utilization of the SCBA based binary blended concrete is more environmental friendly than the respective concrete. So, indicating its potential for its practical application as well. So, thank you.
In conclusion, with reference to AP state concretes, what is it is concrete everywhere, right?
Why you choose?
Concrete is concrete, right?
Yeah.
Why it is AP state concrete?
Okay, AP state means Andhra Pradesh, right?
No, but why? Why? Question is why?
Why only AP state?
Why not all over India?
No, SCBA is more produced in Andhra Pradesh state. So depending on the SCBA availability, I have taken a case study. Yeah, state specific. Yeah, it's a case. No, the case study is.
The property of that package is very.
Yeah, it's based on the availability.
Thank you.
Thank you. Dr. Rao has just anyway, from the front.
I request Dr. S.P. Anchuri to felicitate our keynote speaker of the day since he has. Thank you.
And he only brought me in ICI. I was
For education, everybody is there.
but you are responsible to bring me to ICI. And she's my daughter. But she knew I brought her. Can I request Dr. Srinivas Rao to join? He taught me
Those are among my students. Thank you. Thank you, sir.
Moving to the next presentation. The topic is the durability performance of sugarcane. Okay. By this session, waste glass powder turning blended concrete by Navnita. Please.
Good afternoon. I'm Navnita, research scholar from BITS Pilani, Hyderabad campus, under the guidance of P.N. Rao, Professor P.N. Rao and Professor Bahurdini. I'm here to present a small portion of my PhD work, Durability Performance of Sugarcane Bagasse Ash and Waste Glass Powder Ternary Blended Concrete. Moving on to the overview, first one is introduction, then materials and methods, result and discussion, and conclusions. Moving on to introduction. So from this pie chart, it is clear that India is the third largest country, which is producing around 7% of the total global carbon dioxide emission. And from this, it is clear that cement is contributing around 5% of the total carbon dioxide. And as per the forecast rise of the cement production, it has been stated that the cement production will reach at a value of 6 gigaton by the end of 2050. What is the problem associated with the cement production? It will mainly consume fossil fuel and the resource depletion, greenhouse gas emission, and it has been reported that 5 to 7% emission is from cement manufacturing. So what is the solution for this one? So we can adopt supplementary cementitious material. So we can broadly classify into agricultural byproducts as well as industrial byproducts. So among this, we are concentrating on bagasse ash and waste powder. So this is a sugar plant. From there, we will extract sugar, and the remaining product is called bagasse. And either we can, the more people are doing is that they will burn it in the open field. So it will again cause pollution. So this is not recommended. So we have to avoid that. So this can be utilized effectively for using electricity. We can in the thermal plant. So we can use in the cogeneration boiler to produce the electricity. So it is an effective method, and the byproduct after the burning of the bagasse is called bagasse ash, and this can be utilized as a supplementary cementitious material. Same way, glass is also producing in tons in all over the world. So this can be utilized as a supplementary cementitious material by powdering it. So moving on to materials and methods. So this is the chemical composition and physical characteristics of the binders. And you can see that bagasse ash and waste glass powder is having more than 70% of. So this is siliceous material. And as per ASTM C618, it is having S plus A plus F value greater than 75%. So, and from XRD diffractometer, is clear that the it is contained amorphous silica. So from the 2 theta value 23 to 34, it is clear. And this is a micrograph of waste glass powder. The morphology of the waste glass powder is irregular and the surface is very smooth. And most of the material are similar, the morphology is similar, like it is irregular. But in the case of the morphology is little different, like it is having prismatic particle, spherical particle, as well as some irregular and elongated particles, and some particles are having unique shape, that is dumbbell shape, and it is rich in silica. So as I mentioned, some elongated particle, these are actually fibrous particle. So the next step to in our mind is whether we need to process it. We need to fibrous particular this particle we have to we can keep the material in the oven drying for 105 degrees Celsius. After that, we can sieve through 300 micron sieve in order to remove this elongated carbon particle through 300 micron sieve. Then we can adopt grinding in order to get a similar fineness of the cement. So this is the mixed proportion adopted for my study. So first one is control concrete. Then we are replacing the cement with bagasse ash at 10-30%, and we are fixing a 10% of bagasse ash. In that, we are again the cement with powder at replacement level of 5, 10, 15%, and similarly we are taking 3% bagasse ash as constant, and we are replacing further with waste glass powder. So these are the testing method adopted in our study. We have 28 and 56 days after the and this is in 33% of H2SO4 solution. After that, we have taken out the sample after 7, 14, 28, 56 and 8 days, and compression test has performed. So moving on to result and discussion. So this is the compressive strength results of bagasse ash and waste glass powder ternary blended concrete. So here you can see that with respect to the placement level of cement bagasse ash, when it reaches the 10%, the compressive strength is more compared to the control concrete. Whenever we are replacing further with bagasse ash, it is getting reduced. So the reduction is mainly because of the dilution effect, and the increment is mainly because of the pozzolanic action. So among all of this specimen, you can see that beaten W5 is performing better, and if you are comparing the control mixture of the beaten W5, beaten W15, B20, W5, and B20 specimen performing better, and in the case B30, it is comparable with the control concrete. So this is the chloride ion penetration resistance of ternary blended concrete. So with respect to the replacement level, the chloride resistance is more. So if you are comparing with control concrete binary as well as it is having durability. So this is the residual compressive strength of specimens immersed in H2SO4. With respect to curing period, the residual compressive strength is decreasing. If you can see that you can see that the binary as well as the ternary blended concrete is performing better, and this is the reaction happening while immersing the specimens in H2SO4. So here bagasse as well as bagasse ash waste glass powder blended mortar exhibiting less calcium leaching compared to the control specimen, and beaten W5 is performing better compared to all others. So this is the mass loss of the specimen immersed in H2SO4. So similar to the compressed respect to the elongated period of exposure, the mass loss is increasing. So the percentage of mass loss is increasing when compared to the control concrete binary as well as the ternary blended concrete is performing better. Western GF is showing amount of mass loss. This is the X-ray diffractogram of bagasse ash and waste glass based ternary blended concrete. So here the reduction in the CHP is clearly mentioned that the addition of bagasse ash and waste glass powder is is helping to the pozzolanic reaction, so it can correlate with a better compressive strength of beaten W5. And this is X-ray diffractogram of sample immersed in H2SO4. So here also you can see the XRD analysis, the formation of gypsum and detrengite, and observe peak of CH and CSH, the breakdown of CH when the specimens are immersed in H2SO4. This is FTI spectroscope samples immersed in H2SO4. So the gypsum formation can be easily identified by the bending vibration of SO4 2 minus 113 789 and 663. So the lower gypsum peak in beaten W5 compared to the control specimen is indicating that it is having higher resistance in H2SO4 attack, H2SO4 solution, and shift of SIO-SI and or SIO-AL asymmetric stretching vibration to higher wave number is mainly attributed to the shifting of weaker bond due to the substitution of calcium 2 plus ion in the attack. So upward shifting is more pronounced in H2SO4 exposed sample, which is indicating the greater AL. So we can conclude that in waste glass powder is improving the compressive strength and reducing the chloride ion permeability, as well as it is giving better resistance to acid attack. This is mainly attributed to the enhanced pozzolanic reaction as well as the refinement. And among them, ternary blended concrete with 10% gas ash and 5% waste glass powder is showing better acidic resistance, retaining higher residual strengths as well as lower mass loss. So from XRD as well as FTR analysis also confirm the formation of gypsum as well as the detrengite, CH breakdown as well as the de-alumination under acid formation while the controlled concrete. Powder improve the durability and effective method for making sustainable ternary blended concrete. Thank you. That we are facing the workability issue. Yes, sir. Still. Here I haven't presented. Yes. So actually, as I mentioned, the coarse fibrous particle, they will absorb more water. That is very porous. So we have to remove that. Then we will get little bit good workability compared to that. Instead of using raw bagasse, we have to process it. So that's. Yeah, sir, it is there. So we have to use the super plastic. I've used it. I have done the rheological part also, sir.
Next presentation by Mr. Ganesh Kumar on Karma rubber. Please, please. Karma rubber as a sustainable alternative to fine aggregates.
Yeah. Yeah, good afternoon everyone. I'm Ganesh Kumar, Research and Development Wing of L&T Constructions, Chennai. Today I'm going to present my work that we have recently conducted on crumb rubber as a sustainable alternate to the fine aggregate in the concrete. So my flow of my presentation will be need of tire recycling and why we need to look after the crumb rubber in the concrete and its performance in mortar and the concrete trials. So looking after what will be the availability of crumb rubber in the India, there is a huge amount of tire waste that is being generated in the Indian conditions as well as the worldwide. Looking the global perspectives, around 1.6 billion new tires are generated every year, and out of which only 1 billion tires are being generated as the waste tires. But the recycling capacity is not as high as that they are being generated as the waste tires, where the recycling is only hardly 10%. Coming to the Indian scenario, every year we are having around a waste tire generation of 15 lakhs, out of which the formal recycling is now being burnt in this where we are impact. So in this study, we have looked after like to replacing them as the fine aggregate in the concrete. In the Indian scenario, the market available crumb rubber is available in two forms, one as the granules and another one as the micronized rubber powder. In the granules form, they are available in a sizes between 1 to 2. Micronized form is for more the turf applications where roads. To the properties of the crumb rubber, they will be having a specific gravity of 1.05, which is a lightweight material, and they will be close to 0.3%, and chemically they will be composed out of carbon with traces of sulfur, silicon, magnesium, and aluminum. The carbon is not a reactive carbon here, so they will be just acting the role of a filler. So initially we have started our study with a fresh state motor studies where we started to replace the fine aggregate, traditional fine aggregate with crumb rubber up to a there was no much because the rubber particles are lighter in weight when you compare it to the crushed sand. So there will be an obvious reduction in the density. Then we have done the compressive strength at 3 different ages, 3, 7 and 28 days. So with increase in the ratio of the crumb rubber, the strength of the motor mix is reduced. Typically there are 3 different reasons. The first thing is the rubber particles are smoother in texture and they are not having a proper ITZ zone. The matrix is not having enough densified ITZ around the rubber particle. So they will be resulting in the decrease in the strength. The second thing is they will be having a zinc stearate, which is an hydrophobic. So it tries to repel the water molecule at its surface and increases the porosity of the mixes, which in a way reduces the strength. So we cannot directly use the market available crumb rubber into the concrete form. So there need to be certain pre-treatments to be done. The commonly done pre-treatment, there are multiple pre-treatments that are already quoted in the literature. Like presently, they even are trying to pre-treat it with a graphene to improve the strength and bring it to as good as the parent material. But in this study, we have used a sodium hydroxide pre-treatment method because it is the cost-effective pre-treatment that can be done. So we have started like finding the optimized dosage of sodium hydroxide that need to be used in order to pre-treat it, and we have come up with a like a simple pre-treatment method where you can you can soak the crumb rubber particles in the sodium hydroxide and then you can wash to the neutral pH and they can be used in the concrete applications. So why we have gone for the sodium hydroxide pre-treatment is it done 2 ways. It changes the physical as well as the chemical nature of the rubber particle. The physical nature, what it does is like it tries to etch the rubber particle and improve the or convert the smoother texture into a more rougher texture, as you can see in the bottom right corner image. The second thing is it converts the zinc stearate, which is hydrophobic form, into a water soluble during our washing process, and it reduces the hydrophobic nature of the rubber particle. So in a way, it will tries to reduce the porosity of the mixes that we will be doing it in the future slides. But we need to come up with like what will be the optimized dosage of sodium hydroxide we need to be used for the things. So we have gone with 5% of NaOH solution, 10% and 15%. And we have, as I have already mentioned, the rubber particles were replaced at 2.5, 5, 7.5 and 10. As you can see it here, we have found out like the optimum dosage with increase in the sodium hydroxide dosage up to 10% increment in the strength when you compare it with the control, but post 10% there was a decrease even at the 2.5% replacement levels or at the 5% replacement levels. This might be due to like over presence of sodium hydroxide will damage the rubber particle. So instead of just stitching it, it might be damaged and we are getting a reduction in strength post the 10% NaOH treatment. But when you look at the higher replacement levels of the crumb rubber, even the pre-treatment is not helping it to improve the strength when you compare it with the control. So what we have concluded is like the maximum replacement of crumb rubber that we can go with the concrete trials will be up to only 5% replacement with a pre-treatment of sodium hydroxide, soaking it at 10%. Upon finding the optimized dosages, we have done a detailed concrete study using the replacement of crumb rubber at 2.5 and 5%, which is a pre-treated crumb rubber, not a normal crumb rubber. So we have taken a base mix and we have done the entire study. So these are the concrete results that we have come up with. Like there will be a slight reduction in the slump. There was not much in the motor trials, but in case of the concrete trials, we have observed like strength of the motor, like strength of the slump of the concrete was reduced by 20 mm, Whereas the air content, you can see it is at par with the control, and there was a slight reduction in the density, as I have already mentioned, because the rubber particles are light in nature. So if you can look after the strength of the concrete, we have done the compressive strength, cylinder strength, and modulus of elasticity. So when you compare it with the control, complete fine aggregate mixes, which is with the crushed sand, there was a reduction in strength by 7 MPa, but irrespective of 2.5 or 5%, the strength reduction was not much. Same thing reflects in the other test results. Then we have done even the durability studies, which will be like more talking about the water permeation, water absorption, and the white intents and the penetration to chlorides. So the trend that we have in all the durability studies is 5% replacement of crumb rubber perform better than the lower replacement level of 2.5. The results were almost comparable with the control, but there was a slightly inferior when compared to the control mixes. All the trials were done at a single water to cementitious ratio. Cementitious ratio, they can be matched with the parent concrete. Why only 5%? Why not 2.5? At 5%, there might be better blocking of the pores caused by the rubber particles, and 5% might not be sufficient enough to block the entire pores. So that is why the 5% might be performing better when you compare it with the lower dosage. The only thing is, it just like only the mix will be inferior of water permeation, because the rubber particles are to penetrate at a higher pressure. But the major interest of us is to use the crumb rubber for improving the structural characteristics of the concrete. So we are working on to study it whether how the rubber incorporation will affect the energy absorption of the concrete mixes or the damping ratio. So we have done a detailed study on energy absorption, and we have compared like how it will be better. So for the energy absorption study, control mix was taken an SFRC, because the normal concrete will fail after the load. It will not give us any elastic nature. So in the control mix, like we have replaced the crumb rubber, we have replaced the fine aggregate with the crumb rubber. So if you can see the results, like we have observed, like incorporation of crumb rubber is like enhancing the energy absorption of the concrete mixes to 10%. Like if you want to achieve a similar 10% improvement with the steel fibers, you need to dose additional 15 kgs of steel fiber in the mix. But same thing can be achieved by dosing 5% of the crumb rubber. So this is one notable change that we can use this material in improving the seismic behavior of the concrete. So damping studies, presently we are undertaking it. It will be like we are presently doing the work, so I am not having those results here. So summarizing all the things, so we have an abundant of crumb rubber available in India. Only thing is, like, instead of using it as a raw crumb rubber, we need to pre-treat and use it. It can be more to improve the damping behavior and energy absorption properties of the concrete. So thank you. Any questions?
Thank you. Any questions? Yes, please.
So you are saying that you are using 5% of the crumb rubber.
Yeah.
So where you will apply this type of concrete?
It can be used for like shotcrete panels where the energy absorption will be critical. So the shotcrete panel will be designed for the energy absorption value rather than the strength. So presently we are dosing around 35-40 kgs of steel fiber to get that energy absorption. We want to optimize the steel fiber by incorporating the crumb rubber for such panels.
So in that shotcrete panels means where that panels will be used?
They will be used where the impact loads will be predominant.
Okay. So now you are getting this crumb rubber, and you are replaced. What is the cost implication on this? Because other than the modulus of elasticity or the deformability properties, the other parameters are not comparable with the conventional concrete. In what way the cost implications is taking it forward?
No, the other parameters are not, I can get your question.
No, the compressive strength, there is no much increase.
No, it is
there is a
slight
modulus
decrease.
of elasticity increase that can be.
Yeah, this type is more suitable where the impact load is only predominant. It will not be applicable for the entire concrete media.
Okay.
Where we need to play the ratio between the steel fibers to get the energy absorption, we are looking the crumb rubber as a better alternative in terms of cost, saving close to around 700 to 800 per panel.
No, in terms of cubic meter.
In terms of cubic meter?
What is the cost?
I have done a panel study, cubic meter I need to look after.
Thank you, sir.
Thank you. I hope that this material can be used in the
Yeah, it can be done.
cashback, yes.
Yeah.
Thank you.
Thank you.
Thank you much. Our next presentation is by Sia on use of sandy waste as a partial replacement of the manufactured sand. Surya.
I am Surya, final student, BTech student from National Engineering College. So I am going to present paper on a critical review on utilization of C&D waste as partial replacement of M sand in concrete. So introduction. So construction industries resource use. Construction sectors consume 40 to 50% of raw materials extracted globally, and high waste generation of C&D waste and river sand depletion is happening. Over mining of river sand, essential for concrete has caused severe environmental damage, and so we are shifted to manufactured sand, and restrictions on river sand is a major problem. So that we have come up with the solution of C&D waste as a sustainable alternative. So current state of C&D waste management. So C&D waste management generation has reached a level of 3 billion tons in journal review, and regional variation in C&D waste there is not substantial with developed of 0.1 ton. So production process of M sand. So M sand is made by crushing parent rock, usually quartzite, and then shaping, grading, and washing the particles to get rid of fines. Then primary, secondary, and tertiary crushing stage will be there, and particle size distribution, shapes, fine contents, and impact value is considered as a qualitative parameters for M sand. So comparative analysis of M sand versus river sand. Concrete with high quality M sand shows comparative superior strength than the river sand, and sustained due to declining river sand availability. So limitations of M sand is angular particles reduce workability and increase water demand. So and higher fines content affects the workability, bleeding behavior, and segregation increase. So environmental impact. So high energy consumption during crushing and processing, and it causes the carbon emissions and land disturbance and ecological impact. And economic factors like availability of quality parent rock and energy and labor cost. Distance between quarries and construction sites is economic factors. And processing of C&D waste. So first we are initially sorting off C&D waste, and then the processing process may happen. And screening operation, vibrating screens are usually to separate crushed into different size fractions. So washing treatments to remove dust, clay, and water soluble impurities. Then mechanical treatment conducted to remove the inorganic pollutants. Recycled fine aggregates. So we are using 30 to 50% RFA replacement with the M sand, and it shows the slump reduction of 15 to 20%. So caused by angularity and high water absorption of RFA. So setting time also minimal impact in percentage of the replacement, and it has the high absorption and hydrated cement particles. Other fresh properties like it increases the bleeding property and higher risk of segregation. So hardened concrete property is RFA. So we are using 2% of RFA strength is typically varied with 5 to 10% of control cost. At 50% is decreased to 25%. Tensile and flexural strength show reductions. Durability concerns like carbonation death and chloride freeze deterioration, sulfate attack sustain. So for that we are coming up with a solution. Key movement methods means water reducing admixtures. We can add a superplus to restore the workability. Supplementary cementitious material like fly ash, GGPS, fume, we can improve the ITZ density and durability. And two-stage mixing approach TSMA pre-mixing FA with part of water. So cement we can add initial of water and to reduce the water absorption. And all pre-treatment methods, pre-soaking to saturated surface condition, and nanosilica or PVA solution to SEZ. So limiting fines, so can limit the fines up to level of 150 microns. Reduce water demand and contaminants. So LCA comparison. So environmental operate this RFA, we can reduce the global potential of 8 to 35%, and cumulative energy demand CED of 6 to 30%, and challenges and limitations. More incorporated, so we can process the coarse recycled aggregate and recycle fine aggregate also. So we are taking up recycled fine aggregate. So in this we can have the challenges of organic matter, chlorides and sulfates, gypsum and hazardous of CND waste. These matters will present potential contaminants in RFA and their effects. So chlorides, marine exposure, access sulfates cause extensive presence of reactives, and alters setting times and reduces early stage, and unnitrated cement particles may cause false set or unexpected stiffening. So variability and control challenges in RFA. So inherent variability in RFA. Variability arises from mixed materials, inconsistent processing and sorting methods, and impact on mixed design more complex and unpredictable. So increased difficulty in quality control and performance, creates hesitation among the producers and willingness to use in structural or safety critical applications. So technical knowledge gaps and research needs. So long-term performance predictions, limited data beyond 5 years, most studies was on yearly stage up to 90 days only, and interaction with chemical admixtures, uncertain effects on admixtures, efficiency dosage, standardized testing methods need to be implemented, and performance-based specification needs for acceptance based on concrete performance. Microstructural understanding need to be improved insight into the interfacial transition zone between RFA and cement paste is required. So regulatory frameworks and policy initiatives. So Europe, we have studied Europe sets 70% recovery target by 2000. Content mandates and certificate system for recycled aggregates. So persisting regulatory gaps means lack of universal quality and performance standards for recycled aggregates, low industry confidence, limiting integration in national codes. So we have done. They have used 20% RFA foundation substructure concrete, and in Netherlands demolition planning enabled with 30% of RFA in structural concrete, and in Sydney Olympia Park, Australia, pavements for RFA replacement 15-20%. And performance.
Surya, conclude, please.
So performance monitoring, okay. Cost benefit analysis, local market, land taping fees and fees, or is a benefit. industry risk perception, because we don't have any specific standards for RFA. So, and economic factors like RFA cost competitive fluctuate with policy, quality assurance complex, and supply chain. Future direction and innovation. Sensor-based sorting we can implement, and thermal treatment and microwaves, carbonation treatment we can, and mechanical chemical hybrid process we can implement. So these are the cases I have done. So these we can able to rectify the economy background, like design for disassembly and recycling and urban mining concept. So key finding is that RFA shows a strong potential as a partial replacement of in concrete. It reduces the natural aggregate consumption, lower carbon footprint, significant landfall diversion. So these are the references. Thank you.
Thank you, Surya. Any questions? Okay, thank you. Now move to the next presentation by Sahu, which is on the engineering performance of 3D printed geopolymer earth exposed to yourself environment. Okay, very nice. Okay.
Good afternoon. My name is Pittabas Sahu. I am working with Professor Saurabh Gupta. Today I am going to present on long-term performance of 3D printable geopolymer stabilized earth. So why it is highly required to understand the long-term performance? Here we have to practically implement the 3D printable materials. It is highly required to understand the long-term performance. That mainly under the natural carbonation, like repeated cycle of wetting and drying under the sun, under rain. So here in this study, exposed to the 3D printable geopolymer stabilized earth-based material utilizing natural clay as fine aggregate. So to exposed on a slanted roof condition. So these are the contents. Mainly three aspects I'll explain here. So what is the role of to improve the 3D printability? Then development of bioretarder to improve the open printing type of 3D printable material. Similar is the long-term performance. So first introducing why I used the laterite soil or the excavated soil here as a fine aggregate replacement. Out of which finds in developing countries, similarly 30 to 40% countries. So annual production is also huge. Means every year we are producing billions of excavated soil, and in China alone it is 2 billion ton. So hardly 20% is getting recycled. So what are recent developments in utilize means developing 3D printable So here in recently in OPC based material, natural clay soil it is replaced by 25% and 50% with fine aggregate and with a binder to aggregate ratio 0.5, and they can able to get up to a 1.2. But it's made up of utilizing OPC in geopolymer based material is highly important to get a low carbon material. So another important aspect is the compressive strength is highly reduced when it is 50% of soil has been utilized instead of 25%, because of this how the long term performance may get this moisture sensitivity. So here, as in methodology, I have utilized my blast furnace slag and fly ash as a binder, and means I have utilized excavated soil and manufactured sand as a fine aggregate replacement. And most importantly, the binder to aggregate ratio I have utilized 1:1 to 1:2 with 4 molar and 8 molar, so that we can able to get a comprehensive idea about the molarity. Our inner mix proportion can be up, that is 1:3. So till now maximum it was develop up to 0.5. So more linear mixture is why it is important. More will be the aggregate. So that is why. So we have developed the 3D printable material. In the soil was 42%. That is helping in to improve the rheological performance. So how it was improving the 3D printability, we'll discuss in the next phase. So to understand the 3D printing aspects, the initial material when it is in the mixer, it should be cohesive in nature. So should have high flow retention so that it may be pumped. Further, when the material is getting extruded 3D printer nozzle, the material should have low viscosity. Suddenly, when material is very cohesive in nature, may have high viscosity. But when the material is getting rotated through the extruder, should possess low viscosity. And when exactly the material is getting should again recover the viscosity, so should have properties. That is why it can able to tolerate the load of the upper layers, and it can be buildable. So how clay is improving properties, we can understand by two important aspects. One is plastic viscosity, another one is thixopy. Here the plastic viscosity, these two are the control mixes. There is no soil, so the plastic viscosity is very high. That is why the material easily cannot be extruded, because it creates a lot of frictional force to extrude. So, but at the same time, when the clay-based materials are getting extruded, they wrap up on the surface of sand particle and lowers the viscosity, and get a very smooth material. And another aspect is safe retention. The safe retention means the of the material with the 40 mm nozzle was very high, 60 mm, but in the clay it is 44 mm. So one more important aspect is thixotropy properties. Here we can mimic the design to the materials in the 3D printing. So here the material is in hopper, very low, means a low rate of shear was applied. Immediately it is higher shear is applied to when the material is in the extruder. Again, the material when it is deposited on the print bed, immediately the speed of the rotation was reduced. So generally here it should possess viscosity, again followed by low viscosity. Again the viscosity should recover. So if you will understand, in control basis the viscosity recovery only 67%. However, when soil based mix, the viscosity recoverability even more than 100%. It performs even better than the clay material. So that buildability of the material has been also tested. So the buildability, we can see in the control mixes, two mixes, the lower buildability events are there. Soil based mixes, the buildability is very high. So but one important aspect is the extrudability of the buildable time was only 35 minutes. So to sir, okay sir. So further we have improved the 3D printability with one bioreactor, that is sucrose, extend the 3D printing time, and so we higher initial, the open printing time was improved by 8 to 9 times. What is the science behind why science behind the improving in 3D printable time and the quality of extrusion? Here the sucrose, which one added as a bioretarder, improves the it produces additional water and also induces negative charge. But at the same time, soil-based material, the open printing time was improved by 8 to 9 times, which was seen by the statistical stress graph. So these are the 3D printable structures we have printed. I can able to print more than continuously 3 hours. This is 1.45 meter structures. So now finally I want to conclude with the long-term performance. So interesting when the sucrose has been added, there is a the shrinkage crack has been reduced. The sucrose lowers the rate of hydration. Because of the lowering of hydration, more dense cashew gel has been formed. Because of this, with the sucrose, we can get a lot of and we can get 44 megapascal of strength. And more interestingly, it is cash gel, and that was performed through NMR data, which was I am not presenting here. And finally concluding, we developed successfully the earth-based geopolymer-based material with a linear mix proportion. And sucrose here, it improves the open printing time. It also performs as a very excellent super plasticizer, means it is producing water. And at the same time, it improves the fresh and hardened properties. And further, the long-term performance also has been improved. Thank you much. And these are my publications. Work through this.
So what is the maximum size of particles that you are using in the earth?
4.75 mm. So I was replacing to sand. So sand size.
So how do you grade this earth materials? Because it has different properties at different locations. So
definitely it is.
In what way it affects your rheology of the mix?
I didn't present here. One of the important properties, that is, one is clay content. One more important is clay minerals. And third one is liquid limit or plastic limit. So first one, already clay content, we have explained that clay content improves the 3D printability. Second important aspect is mineral. Generally here we are more should rely on kaolinite based mineral because they are more stable. Third one is liquid limit. So the material shouldn't have much higher liquid limit, means the liquid limit because of wet plastic limit absorbs water, because of absorb water when the metal is getting extruded, helps in means expulsion of water, that is lowering the means viscosity to fix. So that is to help to
reduce the shrinkage issues now.
This is introduced the shrinkage issue mainly at the initial stage. The shrinkage issue was reduced by the addition of this sucrose based retarder. So if the initial reaction can be controlled, means the shrinkage can be reduced. So the shrinkage can be reduced by 2 and initial higher strength. If the material have higher strength, material can the shrinkage can be reduced. We have incorporated that sucrose to be incorporated, so the cash gel can be reduced. Here generally other material here what more than 7,000 to 8,000 microstrain of shrinkage.
Thank you, sir. So, thank you.
Thank you, sir.
Other project, not. Yeah, please.
Good afternoon, everyone, and thank you for staying for my presentation. My name is Vislav Haripan. I'm from IIT Madras. I work with Professor Ravindra Gettu and Manu Santanam. And my topic is concrete fibers as an extender in 3D printing concrete formulation. So this is overview of my presentation. I talk about the introduction, then a procedure for open time assessment, which is open time is the workability retention. It's a time period during which you are able to print a smoother extrusion of the material. It's mix open time, mix duration during which it has the period during which you are able to extrude the material without any surface defect. So you can see if there is shorter printability window, so there will results in the rougher surface texture. And here in printability, I use the extrudability and its extrudability and buildability. I will use this definition in further presentation. Then I'll talk about the rheological performance, then conclusion. So construction demolition waste, it generates around 750 million metric tons of construction and demolition waste. So among it, 23% is the concrete waste. It is recycled, adopting different methods to used as a different types of aggregates back into the construction. In the same process, it generates 20 to 30% of the waste concrete fines. These fines are less than 300 micron, which has the potential to cause land and air pollution. This is not going back into the construction, but it has the advantage. It has the calcium oxide and any other oxide that can be taken, oxide and other hydrated phases it has can be made reactive by carbonation. And parallelly, 3D printing concrete also grow in the market, and by 2029, it is projected at 31% it will grow. And it requires huge amount of fine material, FY40 to 900 kg per meter cube. As the binder production process is a carbon intensive method, again it contributes to 5 to 8% of global CO2 emission. And for reaching this property, again extrudability and buildability, the requirement for the reactive material is very important, because as one layer is printed about the other layer, the already printed layer able to take the load of the subsequent layer during the printing. Very short time of printing. So this is the mix I have developed. The reference mix I have used here is a very low carbon material. We talk about the LC3 here. The similar mix I have developed, which is composed of 55% OPC and 45% of LC2. So I am trying to make this mix even low carbon, and I am trying to use this mix, and also I am trying to use this waste concrete fines by making this together with the carbon sequestration. So I am trying to carbon capture also with the waste concrete fines. So I am trying to replace the waste concrete fines 30, 50 and percentage with the LC2, and again I am trying to replace OPC up to 30% after a donation of waste concrete fines. So the material is, the waste concrete fines is a finer material, but I am just checking to see how it affects the optimum particle packing. So Anderson model is used here. So as the replacement goes on, the D90, D50 and D10 sizes shift towards the optimal packing curve. And whereas the 100% replacement, it shows the coarser skeleton. So this is the microstructure of the waste concrete fines after and before carbonation. And after carbonation, it showed the huge amount of the calcium carbonate together with the aluminosilica gel, which is reactive in nature, and the same observed from the FTIR oils also. So this is the specimen which I printed to assess the open time performance, and this is the period that I adopted, and there are no procedure there for assessing the open time. This is the framework I made, and why I adopted this specimen I will explain in further in my presentation. So this is I printed every half an time, because the open time is the duration during which the concrete able to print, the printer able to print the material. So that's why I am trying to print the material at different time interval and see how the surface defects are forming on the surface. So and up to 2 hours are printed, and a few mixes I have found that it is not extrudable in around the 2 hours. And so parallelly I try to measure the flow table value and the static yield stress. Static yield stress is the minimum stress required to deform the material. So what I found is the material with the 160 mm and the yield stress is 2.4 is found the defect free, as you see in the previous slide, and the flow value 140 mm and the yield stress is greater than 3.7 kPa is not found to non-extrudable. And the thing is, the uncarbonated mixer showed the lower flow table value compared to the carbonated mixes, and the static yield stress for the uncarbonated mixes is higher compared to the carbonated mixer in the initial stages. And again, this table shows two more parameters which I used for assessing the open time. It's RPM and also surface density index. The RPM is the amount of the pressure to the extruder to extrude the material that is to maintain the target layer dimension. Again, is the number of the surface defects that are formed on the layers during printing, that is more than the 5 mm per total perimeter, outer perimeter length of the specimen. So when it is maintained between 3 mm and the static yield stress less than 2.44, it shows the surface defects showed less than 5. Per parameter, I made this table. So the mixes which showed the flow values 160 mm and the static yield stress 2.4 throughout the printable window, which is greater than 90. So that mix is called performing excellent in terms of open time. And if it is showing this range between the 60 to 90 minutes, it showed the good. And if it is between half an hour to 1 hour, then it is acceptable. Then if it is showing the less than half an hour, then it's poor. And if it is less than 14 minutes, it's unprintable because you don't get time to print. And the similar way, the mixers performed well after carbonation, and after carbonation, some mixers even performed very good category. And this is because of the calcium hydroxide, the calcium oxide which is forming carbonate during the process reduce the water absorption by filling the pores which are present in the waste concrete fines. And here you can see the mixers with the carbonated has a lower surface. So these are the few more properties that are very important for printing. So static yield stress and dynamic yield stress and the thixotropy and structuration. So with this carbonation, all this property which increase the reactivity of the material, and together it actually increases the buildability property of the mixes. And the advantages of the utilizing of waste concrete fines is promote circular economy, and together I am doing the carbonation so it can sequestrate CO2. And this formation of the reactive products during the carbonation, the calcium carbonate and alumina silica gel will result in the higher structuration rate, which ultimately contributing the higher buildability. Thank you.
Thank you. Any questions? Thank you.
Thank you.
Next presentation is by Uwais Ahmed. Yourself, okay, please. On how to assess the pressurizing force is the main issue. Thank you. Sure, okay.
Good afternoon. Myself, Uwais Ahmed, Senior Principal Scientist, CSIR SCRC. The title is on Residual Pre-stress Evaluation in Pre-stress Concrete Structures using a flat jack technique, the concepts and challenges that we are facing for this technique that I will be describing it. So my outline of the presentation will be like this. First about what is residual pre-stress measurement, and then about the flat jack, its working principles and its applications. Then what is the motivation to be used use this flat jack in pre-stress concrete, then challenges that is faced using the flat jack in the pre-stress concrete, and what are the methodological modifications taken towards those challenges, and finally discussions on the studies conducted, and with the summary and conclusion. So we all know the pre-stress concrete is extensively used for long span structures, especially in bridges, because to counteract the tensile stress. So the tensioned high strength steel tendons is applied on the concrete, which creates a compressive stresses, which counteracts the tensional forces that is developed in the concrete. So mainly the structural performance of this pre-stress concrete is structures are mainly relied on this pre-stress force. That is, even though you have lot of advantages like full compressive strength, lesser deflection, lesser risk of corrosion, reduction in sulfate, the only challenges is loss. How this loss is very, very important. Then, why need to measure the residual pre-stress? Why we have to evaluate the loss? to ensure whether the structure is performing its function or not. If it is loss is reduced, then it leads to more deformation, it leads to tensile stresses. There are many techniques that has been used to evaluate the pre-stress losses, but those are all indirect techniques which does not tell the pure information about the existing pre-stress forces. So the methods of classifying this pre-stress loss is categorized into three. One is destructive method, the non-destructive method, and the hybrid method. Destructive method is nothing but when you do the test on that particular material or the member is no way functional after the test. So this includes load test or any destructive. So non-destructive test we classify into two. One is experimental, another one is numerical or analytical. So there are some methods, experimental, strain cone methods, numerical methods, vibration studies method, or a reveal the value of residual pre-stress, but based on the information or the assumptions we fed in the input. And finally, also there are some hybrid models which tells about the combination of both experimental and numerical methods. So the main gap is existing entity methods are indirect and lack precision for pre-stress loss evaluation, which motivates exploring the flat jack method. Now we will come to flat jack method. Flat jack method is an old technique which is extensively used for measuring the in situ stress in masonry structures or rock mechanics. So what it tells is that whatever the masonry structures that is having a compressive stress which is inbuilt due to the or rock mechanics because of its own weight. So these techniques can be used to identify what is the existing stresses in the concrete. It is a very simple bladder. What it does is make a slot in the model. So once the slot is made, the compressive stress will try to compress that slot. So the deformation before and after the cut is measured, and we insert this flat jack bladder to restore the original deformation to see what is the pressure that is applied on the structure. So there is a relation between this applied. So why evaluate residual pre-stress? For a long time, it relaxes. Then the force in the rubber band reduces. Because of this, the compressive stresses reduces, tensile stress increases, cracking and deterioration happens. So why flat jack? Because there are many techniques, hybrid, non-destructive. So what happens? These techniques needs input information. Whatever you feed inside, it will give the results based on the input data. So now this flat jack method does not need any input. It can access where the tendons, it can be used other than the tendon areas. It is less destructive, simple slot, 5 mm or 4 mm. So why? What is the problem that we are facing? What is the need, challenges that flat jack method in the concrete structures? First, masonry structures are stiff. Concrete structures are more stiff. It requires higher pressure because masonry structures, the stresses are around 2 MPa, 3 MPa, 4 MPa. But in concrete, it is 15 to 20 MPa. Reinforcement limits. There are reinforcement in the concrete structure. There is no reinforcement. And because of the tendon profiles, complex profiles, so you will be having a non-uniform stress at many locations. So the need for method adaptation is standard flat jack procedures are not suitable for PSC, and specific issues like stiffness reinforcement and requires modifications including the slot geometry, what is the size of flat jack and how to cut the slots and what is the design and calibration. So based on this, like reinforcement, normally you see the reinforcement minimum 100 mm to 150 mm. Whereas in case of pre-stress, the reinforcement is not a major player or major component in taking the loads, only the pre-stressing force. So in that case, the minimum spacing of the reinforcement will be 150 mm. So slot size or maximum flat jack size is restricted to 150 mm. Other aspects. So now if I want to use it in concrete, I have to use a higher material, higher strength material which has more removable properties. Second. Third, and what is the shape I have to use? It's purely based on the cutting. Either you use chainsaw cutting or a circular saw cutting. So based on this, the dimensional scenario. No. Before applying the flat jack in the concrete, so we have to test what is the relations that the pressure applied and what is the relation that is stress available. So based on this, a simple test using a CTM has been done to evaluate what is the force that I am applying flat jack bladder and what is the force that is recorded in the system. So based on this, a graph is plotted and the slope is 0.36. That means that if I apply 1 MPa of pressure in the flat jack, it restores 0.36 MPa in the concrete structure. So finally, the adopted modification is, this is the conventional flat jack that is being used in the masonry or rock mechanics, which has been transformed into the flat jack, which is suiting the requirements of pre-stress concrete structures. So address the challenges by modifying the size of shape of the flat jack. The overview finding is adapting flat jack method for a pre-stress concrete measurement. It will tell you the direct residual stresses in that concrete. Then address stiffness and reinforcement interference by resizing or by new flat jack dimensions, and more accurate than any NDT methods. Where this is direct stress measurement with minimal invasiveness used for aiding in service pre-stress concrete structures. Supports maintenance, planning and life cycle assessments. Once know what is the value of residual pre-stress, you will be able to do the strengthening or retrofitting schemes. Nowadays, pre-stressing concrete are strengthened based on a random numbers. So this will give you a clear idea about what, because random numbers maybe sometimes it is lesser, we will damage to us. So modified flat jack technique is a practical, reliable solution for pre-stress concrete evaluation. Thank you.
You. Any questions? Thank you.
NDT tests you are doing experiment in the laboratory, or you will in the live structures you can do it?
Sir, this is a part of the study which you have done it. This will be conducted on the live structures only. Yes, sir. So at the existing in-service structures with this 25 years, 30 years, we measure the pre-stress loss 40%, 50%, 60%. So this technique will be directly adopted at the site to measure what is the stress in the pre-stress.
But
so
once you do that NDT, that will not be useful, no? That structure will get damaged.
So no, sir. I make small slit. It is like taking a blood samples from our veins. It is like 4 mm by 50 mm. That is a slot size. That slot size will be filled. Or if it is left open also, it does not affect the structural performance.
Thank you.
Thank you, sir.
Thank you. The last paper in this session is on RCA by Mr. Manvendra Verma. He is not there. Okay, thank you. That's all in this session. I hand over to.
That was a wonderful session. All the presenters that was a wonderful session. Now I would request Engineer Namana Vamal Rao sir to honor and felicitate the session chair, Dr. Rajiv Goyal. Sir. No.
Can you change the background?
Change the background.
Okay. 1 second.
Yes. Yes, sir. Thank you. Now we'll break for the session and this will start at scheduled time, 2:30 p.m. in Kohinoor.
Good evening, one and all. Myself, Sheikh Lal Mohiddin, research scholar from NIT Warangal under the supervision of Dr. D. Raviprasad sir. So my preliminary study is machine learning techniques for compressive strength production of recycled aggregate concrete containing mineral additives. These are my contents. And coming to the introduction, we all know that concrete is the most widely used building material and it is essential to the strength and the performance of critical infrastructure. Traditionally, optimizing the proportion of major components like cement, water cement ratio, aggregate, sand, etc. as relied on empirical and trial and error process. So these are time consuming and resource intensive. So we are looking at advanced computer algorithms that can optimize the mix design and predict the performance of the concrete accuracy. And we all know that the relationship between the various input parameters and the concrete behavior is often complex and non-linearity. So the traditional statistical methods may struggle to capture these relationships. So as recent onwards, machine learning is an effective tool for resolving these problems, and it should produce more accurate when compared to the conventional statistical techniques. And coming to my objectives, first one is to determine the most influencing parameters which has an impact on the strength properties, and the second one is to identify the best ML models for predicting the strength properties of recycled aggregate based concrete, and the third one is to evaluate the predicted performance of specialized ML algorithms using the statistical evolution metrics nothing but R square, root mean square error and the mean absolute error, and the final one is to analyze the model predictions using the SHAP analysis, which is nothing but Shapley additive explanations, to understand the contributes of each input variables. Coming to the methodology, first step is data collection, which is nothing but the process began to collect the experimental or literature data based on the recycled aggregate based concrete. Second one is data pre-processing, which is nothing but prepared the raw data to the machine learning algorithms. In these three techniques are there. One is handling missing data, normalized, which is nothing but standard the all input parameters to avoid the bias and reduce the generalizability. And the third one is feature selection and engineering out of from this correlation analysis and regression feature elimination to avoid the bias. And next step is model development and evolution. In this we considered 6 algorithms: linear regression, decision tree, random forest, support vector mission, gradient boosting, and artificial neural networks. After that, the parameters are to be tuned by using different techniques, nothing but grid search, random search, and the cross validation to find out the optimal best fitting parameters. Then we have to evaluate the model by using the evaluation matrix R square, root mean square error, and the mean absolute error. Then we have to interpret the analysis by using the SHAP analysis, how the each input feature contributes. Next, coming to the resultant discussions, the first one is correlation matrix. From this correlation matrix, we have to identify the input parameters, how it should contribute to the target variable. From my analysis, curing days and the supplementary cementinous material exhibit the good correlation with a coefficient of 0.77 and 0.67. And recycled aggregate shows a negative correlation, which is nothing but usage of recycled aggregate contain more, then automatically tends to decreases the compressive strength. And the another important intercorrelations relation between water and cement ratio, which is nothing but coefficient of correlation R value is 0.77, which shows that we have to increase the cement content, then automatically the water also increases to maintain the workability. So by adding more water, definitely it leads to decreases the compressive strength. Next one is strong positive correlation between the water and SCM. It should also SCM required more water during the mixing. Next, coming to next phase, these are the regression fit lines, which shows the how the actual and predicted values will show a deviation between the actual and the predicted values for the training test and the testing test. These are linear regression, decision tree, SVM, and gradient boosting, random forest, artificial neural network. Out of all these 6, SVM perform the more accuracy when compared to the remaining models. Next one is performance of algorithms on the data sets. So I consider the 6 algorithms. From all those 6 algorithms, the training and testing for the all evolution metrics. From these results, it showed the support vector mission shows the more accuracy when compared to the remaining algorithms, 96% accuracy, followed by the decision tree having an R square of 0.89. After that, ANN also performed somewhat better, 0.88. From all these, random forest will show the less accuracy when compared to the remaining models. Next one is sharp analysis. From this, we have to identify how each input parameters contribute to the target strength. From this, the most influencing parameters, important parameters are natural coarse aggregate, recycled coarse aggregate, sand and cement. And the curing days and superplastizers show the less important parameters because curing days has a limited variation in consider the data set, and the superplastizer most probably affecting workability rather than the strength. Coming to the conclusion, out of all 6 algorithms, support vector mission got the more accuracy when compared to the remaining, followed by decision tree, and random forest which shows a less accuracy when compared to the remaining. When coming to the algorithms, so remaining algorithms linear regression, nothing but it shows some deviation indicating that the overfitting when compared to the algorithms, like similar to gradient boosting as well as random forest also shows a lack of flexibility while capturing the complicated patterns. From sharp analysis, the most influencing parameters nothing but natural coarse aggregate, recycled coarse aggregate, sand and cement. Thank you. MATLAB, sir. MATLAB. Yes, sir. In my college, I think license version is there, so we can utilize it from my college source. In correlation matrix, okay, sir. And output. Okay. 220, sir. Not sufficient, sir, but this is my preliminary study. Later we can go with more number of samples. 80% was contributed for training and the 20% for testing.
But what about validation?
So validation which is similar to training only, sir.
See, the thing is, it's ideal that if we can make 70, 50, 50,
okay.
You will get, because among all, and another thing is you have not tried XG boosting.
Yes, this is only initial,
yeah.
Yes, sir. Okay, sir, okay.
Tried out and
okay, sir.
got very good things.
Okay, sir.
Outcome is very good if you use XG boost.
Okay, sir. Thank you, sir.
Good job.
Thank you, sir.
Yeah, next, Mr. Vishnu. Yeah.
Good evening to one and all. Myself K. Vishnu, lecturer in JN Government Polytechnic, Ramantapur, Hyderabad, and Professor Bhikshma sir from Osmania University, Jagannath Rao sir from CVIT College, and P. Yugender from Gani Khan Engineering College, Malda, West Bengal. And today I am going to present evaluation of mechanical performance of self-curing concrete incorporating PEG 400 and GGBS as partial cement replacement. In this contains introduction, literature review, experimental program, result and discussions, conclusion and references. So as we all know, concrete is a composite material consists of the cement, sand and coarse aggregate and water. Here the cement is one of the constant material which have the problem that is production of the cement is a major source of carbon dioxide emission, which is more creating and destroying the environmental. And it is one more disadvantage is it consumes more natural resources. Uh, these are the problems with the cement. And next, one more important material is the water. When you water is essential to gain the strength of concrete by hydration, and more quantity of the water is wasting by traditional curing methods, and moreover errors in the traditional curing methods, and these two can be some of the errors are eliminated by introducing alternative materials to Portland cement, and internal curing agents to the curing methods. And industrial byproducts are used, some of them are fly ash, silica fume, GGBS, and waste glass as supplementary cementitious material helps to reduce cement consumption and support effective waste management. And in place of water curing, self-curing concrete uses materials such as polyethylene glycol, super absorbent polymers, and lightweight aggregates to retain additional moisture within the mix. And these are the literature reviews. Some of them are on GGBS. And these are the literature reviews on PEG, that is self-curing concrete, PEG dosage. And in my experimental program, these are the materials used: ordinary Portland cement, that is 53 grade cement, and GGBS blast furnace, ground granulate, and aggregate in this fine aggregate, coarse aggregate, fine aggregate, zone 2 fine aggregate as per IS 383, and the water, polyethylene glycol 400, which is water soluble polymer, and super plasticizer, that is Conflast SP 430. And this is the mixed proportions. I have taken only 3 grades, M20, M40, M60. And in this last two columns were indicates the variation of the GGBS and polyethylene glycol. GGBS is varying from 0 to 40%, and polyethylene glycol is varying from 0 to 2%. And this is the mix combinations, total 25 mix combinations are there. So total indicate first term indicates the mix type, C is cement, and next number indicates the GGBS, and next number indicates the polyethylene glycol. So GGBS is the replacement, PEG is the additional material to the mix types. And after all the mix types performed in the laboratory, workability was checked with the conventional concrete. So slump values are observed: 90 for M20, 77 for M40, and 55 mm for M60 grade concrete. And remaining, those are the for conventional concrete, and remaining are varying from 90 to 117 for M20 concrete, 77 to 110 for M40 concrete, 55 to 86 for M60 concrete. And this is the compressive strength of the 3 grades of concretes, and all 25 mixes are plotted. So here it is M60 grade, we got highest at C10, C10G1P, and M40 and M60 I got at 10, and see here. For M20 grade concrete, we got C20G1.5P as the highest results compressive strength, that is 31.91 Newton per mm square, and that is 14.70% more compared to the conventional concrete. And similarly for M40 grade of concrete, M20G1.5P, I got the value 55.62. And M60 grade of concrete, I got the highest value at C10G1.P. So this is the flexural strength of the concrete for similar trend. Maximum I got at M20 I got for C20G1.1P, and for M60 C10G1P. So this is also similar split tensile strength. and variation of the strength with the addition of the polyethylene glycol and GGBS is because of the polyethylene glycol is a hydrophilic material which forms the a bond with the water when it is added to water, and it will be releases the water at the time of requirement cement hydration process. So due to this, the sufficient moisture is inside available to get the strength, and GGBS is the one of the industrial iron industry waste material, and which is having similar kind of properties of cement, which improves the density of the concrete by forming additional calcium silicate hydrous CHSL, and it is also fill the micro structure. And this is the how PEG reacts with the water, and how it was reducing. When it is reacts with the water, it forms a hydrogen bond, and when heat of hydration increases, that bond will breaks and the water will be given to the cement. And final conclusion, for self-curing concrete containing GGBS grades M20, M40, M60, my compressive strength is increased by 14.7, 13.4 and 11% respectively. Similarly, flexural strength of the concrete increased by 13.4, 12% and 9.4%. Splitting tensile strength 14.5, 13% and 10.6%. So final conclusion is optimum quantities of the polyethylene glycol 400 and GGBS were obtained. 20% in M20 grade, M40 grade, and PEG 1.5% in M20 grade and M40 grade. And coming to the M60 grade, 10% of the GGBS and 1% of the PEG, I got the maximum. So by using these two additional material in concrete, overall strength of the concrete was improved by 10 to 15%.
Okay.
Sir.
You have any question? So if you see M20, M40 and M60,
Sir.
for M20 and M40, you got it at a almost same mix, right? Like
Yes,
for the
sir.
same combination of
Yes, sir.
dosages. Why do you think it has changed for M60?
Because M60 is the high grade of the concrete, it requires more cementitious material. So because of that.
No, but you are, that is true. But if you see C1.5G
Yes, sir.
is constant for almost first two mixes, M20 and M40.
Yes, sir.
But it got changed to M60, and where you got it only at 1P.
Yes, sir. 1P, 1% of that.
So I think maybe you need to look into it, why it happened.
Okay, sir.
And because your work is on self-curing,
Yes, sir.
you have not spoken anything about curing part. So like how did you cure? Did you cure it in the water, or you have not cured it at all?
Not, sir. In the laboratory, conventional part will be cured by the water, and the remaining are not cured. Only it is exposed to the moisture content and environment.
Fine. Okay.
Thank you.
Thanks. Yeah. Next, Chaitanya. Yeah.
Good evening, everyone. My name is G. Krishna Chaitanya. I am from Chaitanya Bharat Institute of Technology. Today I am going to present about my research topic about evaluation of concrete beams reinforced with glass fiber reinforced polymer bars under static loading, under the guidance of Harshadujan Chaudhary, K. Jagannatha sir, and N.R. Dakshinamurthy. And these are the table of contents I am going to discuss for the next few minutes. We all know that durability and service life of the concrete has been affected mostly due to corrosion. So corrosion of the steel reduces durability and service life of RC structures. So this create a critical need for corrosion related reinforcement alternative. So many research work has been done to enhance the durability and service life of the structures by replacing steel reinforcement by alternatives such as FRP bars, stainless steel bars, and epoxy coated bars. And so we by many literature reviews and everything, we proposed a new solution for replacing of steel reinforcement by GFRP, as they are non-corrosive and high strength, durable, making them ideal for harsh environments. But the new problem arises here is the brittleness of the GFRP bars, as they are unlike steel, they behave linearly elastic and brittle in nature. So these are the stress strain graphs. We all know that GFRP bars behave linearly elastic, as they don't have any yield point, unlike steel. So these are literature reviews we gone through, like Habib et al. In the year 2008 has many of the literature reviews mainly told that replacing of steel reinforcement with GFRP bars, they observed replacing GFRP with steel exhibits more cracks, wider cracks when compared to steel reinforcement. So this, as every literature review and many things told us that replacing will only serviceability and durability can be evaluated, but no one spoke about the secondary reinforcement, introduction of secondary reinforcement into the RCC structures. So this idea is our scope of the project, and we introduced glass fibers as a secondary reinforcement into the concrete. So here in our objective of the study is to evaluate the beams reinforced with GFRP along with some volume fraction of glass fibers, and evaluate the ultimate load carrying capacity, first crack load and load displacement curves, and displacement ductility of the beams. M25 grade concrete of using OPC grade 53 cement and natural sand crushed stone aggregate of varying size up to 20 mm has been used, and GFRP bars has been only used as longitudinal reinforcement, whereas Fe250 has been used as transverse reinforcement, and 1.5% by volume fraction of concrete glass fibers has been added to the concrete, and these are mixed design details we used for the study. And test specimen size of beams of 150 mm, 150 mm, 2000 mm were used for the study. We used 4 beams categorized into 2 groups based on the percentage reinforcement of GFRP. In group A, beam AG is in both groups, beam AG and BG has been reinforced with 4 GFRPs, only GFRP bars, while beam AGF and BGF has been reinforced with GFRP bars along with glass fibers of 1.5% volume fraction of concrete. So in group A beams, we used only 4% GFRP bars, as our literature review told that increasing of GFRP reinforcement enhances the load carrying capacity of the beams. So we categorized it into 2 beams, where 4 GFRP bars with longitudinal reinforcement ratio of 1.39% has been used in group A, while group B beams are reinforced with 6 GFRP bars, 3 at top and 3 at bottom, with a longitudinal reinforcement of 2.09%. And test beams were casted and queued for 28 days, and beams were tested under servo controlled hydraulic jack of 50 kilonewtons capacity under rate of loading of 0.02 mm per second until failure, and at 25% in post peak displacement phase we marked the failure. And these are the crack patterns observed in the beams. While beam AG, as it is reinforced only with GFRP bars, it exhibited wider cracks. Both beam AG and BG exhibited wider cracks when compared to beam AGF and BGF, as the crack width has been decreased when the glass fibers has been introduced into the concrete. And these are the load displacement graphs. As we can see that beam AGF and beam BGF both exhibited higher loads when compared to beams AG and BG due to the tensile stress distribution has been distributed by glass fibers. And these are the test results. As we can see that in literature reviews, we observed that increasing of GFRP reinforcement increases the load carrying capacity, which can be justified here as AG and BG can be compared. Peak loads has been increased, but the real part is addition of fibers has been increased, first crack load and peak load along with displacement ductility. As we all know that displacement ductility is a ratio of ultimate displacement to the yield displacement. So displacement ductility has also increased as by introduction of glass fibers. So results and discussions here. control beams, as we can see that AG and BG exhibited major flexural cracks with significantly larger widths, while glass fiber introduced fiber beams have been showed only minor and distributed cracks. So here we can conclude that glass fibers acted as a micro reinforcement due to the bridging action and the tensile stress distributions due to glass fibers has significantly increased all the crack loads, peak loads, and displacement ductility. Here, all test specimens has been failed due to ductile flexure failure. Here, significantly, cracking load has been increased by a percentage of 54 to 70, and ultimate peak load has been increased up to 60%. And I can conclude that incorporation of glass fibers in concrete with GFRP was successfully mitigated the primary disadvantage of GFRP, that is brittleness and wider cracks. These are the references.
Any questions from anyone? Okay, so I have a question. So what is the diameter of this stirrup?
12 mm.
Stirrup. Transverse reinforcement.
8 mm.
And the main bars?
Main bars 12 mm. GFRP 12 mm.
So how did you tie the 8 mm stirrup, which is made up of steel, to a 12 mm bar, which is made up of FRP?
Normal J-wire.
But the compatibility, it's a challenge, isn't it?
Yes, sir.
Yeah. Okay. And top reinforcement also 12?
Yes, sir. Both top and bottom.
So you maintained uniform reinforcement at both bottom top.
Yes,
Why do you think so? It has to be maintained same at tension as well as compression?
We choose to make that. Actually,
did you design the beam or it's just random
No, sir.
placement?
Actually, there is another part of the project which is like comparison of steel, conventional steel with GFRP. So here what we mainly focused is on GFRP with glass fibers. So as we all know, many of the literature reviews has been done on steel and GFRP comparison. So we want to just move ahead and compare GFRP and glass fiber. So that's our motive.
Okay, fine. Thanks.
Thank you.
Thank you, everyone. As we have missed to give the formal introduction to the session chair in the starting due to some technical reasons, I request your appreciation for making it possible now. So, Dr. Sri Kalyana Ramajoshila is an associate professor in the Smart and Sustainable Materials Lab at Department of Civil Engineering at Mahindra University, Hyderabad. He holds a PhD from BITS Pilani, Hyderabad campus and completed his MTech and BTech in Civil Engineering from VR Siddhartha Engineering College, Vijayawada. Before joining Mahindra University, he served as an assistant professor at BITS Pilani, Hyderabad campus and VR Siddhartha Engineering College, and later as R&D cell coordinator and associate professor at VBIT, Hyderabad. His research focuses on low-cost precast wall panels, rheology of ultra-high performance and 3D printed concrete, construction project risk assessment, and repair and rehabilitation of concrete structures. He is actively involved in developing smart and sustainable construction materials. Dr. Kalyanaram Joshila is a young member of RILEM and a life member of the Indian Concrete Institute, Indian Association of Bridge Engineers, and the Society for Reliability and Safety. He also holds a professional recognition as a Level 1 Certified Risk Management Professional from IRM UK, a Bentley Distinguished Educator, and a Construction Life Cycle Assessment Specialist from One Click LCA. I request Dr. S. Gangaram and N. Maulrao sir to kindly come and felicitate Dr. Kalyan Ram Joshila sir.